Hello everyone, my name is Yuyang Jin from Tsinghua University. My mentor is Professor Zhai. It's my pleasure to present our work on PPOP 22. My research interests are performance analysis and optimization. This work is PerFlow, a domain-specific framework for automatic performance analysis of parallel applications. Now, let me present our work. The scales of modern supercomputers become larger and larger, which bring unprecedented growth of computing power. For example, the theoretical peak performance of Gaku is over 500 petaflops. However, parallel programs cannot efficiently use the computing power of modern supercomputers. HPCG is a widely used benchmark which is intended to model the data access patterns of real-world applications. This figure shows the comparison of measured performance of HPCG and theoretical peak performance of top-ranked supercomputers in top 500 list. The average efficiency of HPCG is only 1.72%. For real-world applications, the efficiency is even lower. Parallel programs are not efficient. So, how to improve performance? There are multiple steps. First, we do performance analysis on a parallel programs and identify performance bugs. Then, we apply optimizations on these performance bugs to get an optimized program. Then, we repeatedly perform these steps until the programs achieve high performance. Performance analysis is one of the key steps, and it is highly useful. It can help identify performance bugs, guide optimization, and also design future HPC systems. But performance analysis scenarios are complex. It is caused by many reasons. First, there are many kinds of performance bugs like load imbalance, network congestion, and resource contention. Besides, the interactions between performance bugs make the performance analysis scenarios more complex. For example, the inter-process communication pattern and intra-process data control dependence. Because of these reasons, performance bugs are deeply hidden. We need in-depth analysis to detect these deeply hidden performance bugs for each scenario. Currently, there are mainly two kinds of approaches. First, general performance analysis tools, including profiling-based tools like HPC Toolkit, MPIP, and OnMap, as well as tracing-based tools like Scala, Vampire, and TAU. These general tools can automatically do some basic analysis, but they still need human efforts for in-depth analysis. Second, task-driven performance analysis approaches. These approaches target on specific scenarios and provide in-depth analysis. However, current approaches cannot cover all scenarios. For new scenarios, developers still need to manually implement analysis tasks, which incurs significant human efforts. So, how to reduce the complexity of implementation? A domain-specific framework for performance analysis is needed. This framework needs to define two key components: an unified representation for describing performance analysis tasks, and unified programming interfaces for accessing programs' performance behavior. How to design these two key components is also the main challenge. We take communication analysis as an example to show the process of performance analysis. To analyze the communication performance, we first run the program with profiling or tracing. After execution, we get communication hotspots and check whether these communications are balanced across different processes. If they are imbalanced, we further check whether the communication sizes are balanced. or check the synchronization time of each process. We observe that the process of performance analysis is a flow diagram. And we find that parallel programs' performance is strongly correlated with dependence, including intra-process control data dependence, inter-thread lock dependence, and inter-process communication dependence. We observe that program is naturally a graph. The dependence is the edge of the graph. Many existing works have leveraged graph analysis for program analysis, like WPerf, Program L, and Cypress. There are two core ideas in PerFlow. The first one is that we represent the step-by-step process of performance analysis as a flow diagram, and it is the main innovation of our work. The second one is that we represent programs' performance behavior as a specific graph. Inspired by previous works, we further define a program abstraction graph and unified programming interfaces based on this graph. Then we introduce the framework of PerFlow. First, there are two-level abstraction in PerFlow. We abstract the performance behavior as a program abstraction graph, PAG, and abstract the process of performance analysis as an analysis flow diagram, AFD. Then we design two-level API. Low-level API is to build AFD vertex based on PAG, and high-level API is to describe user-defined in-depth performance analysis based on AFD. Now, we further introduce each component. First, we introduce how to leverage hybrid static dynamic analysis to generate a program abstraction graph. Hybrid static dynamic analysis is based on binary instead of source code, which means it is more suitable for production environments. At the static phase, we extract a program structure. At the dynamic phase, we use a sampling-based profiling technique to collect performance data. Finally, we combine program structure and performance data to generate a PAG. Here we give the definition of PAG. The vertex of PAG represents code snippet or program structure, such as function, loop, and call. The edge of PAG represents dependence, including intra-process data control dependence, inter-thread lock dependence, and inter-process communication dependence. And there are two views of PAG. Top-down view is used for comparison of multiple program runs. Parallel view is used for detecting complex performance bugs inside a program run. Then we introduce how to build two views of PAG. For the example program on the left side, we first perform intra-procedure analysis to get a program structure of each function. Then we perform inter-procedure analysis to combine all functions structure as a program structure with function call relationships. Finally, we embed performance data on the program structure to generate a top-down view of PAG. Parallel view is generated based on top-down view. We first perform pre-order traversal to get each thread's execution flow. Then we perform inter-thread analysis to add inter-thread dependence between thread execution flow. Finally, we perform inter-process analysis to add inter-process communications to generate a parallel view of PAG. Then we introduce the definition of AFD. We represent the step-by-step process of performance analysis as a flow diagram. There are two elements in AFD. First, pass is the operation on an AFD vertex. It performs a basic analysis subtask. PerFlow provides built-in passes and support developing user-defined passes with low-level API. Set is data flowing through an AFD edge. It is an intermediate result of analysis subtasks, as well as the input and output of passes. Set consists of PAG vertex and edge. For example, in this figure, there are some PAG vertices in the input set. The pass updates the content of input set and outputs a new set. Then we introduce the low-level API. Low-level API is designed for building passes to analyze PAG. The performance behavior is represented as a graph. Thus, graph-related operations can be used to access and analyze performance behavior. There are three kinds of low-level API. The first one is graph operations, such as accessing the attributes of PAG vertices and edges, searching neighbors of a vertex, searching the source or destination vertex of an edge. The second one is graph algorithms, such as BFS, pattern matching, communication detection, and so on. Third, set operations, such as sorting, filtering, intersection, union, and so on. Then we take three examples to show how to use low-level API to build passes. The first example is a hotspot detection pass. It is to identify the code snippets with the highest value of specific metrics. For example, hotspot detection identifies the hotspot vertices in the PAG. Here is the code for the hotspot detection pass. Sort by and top are set operations, and the VM is a graph operation to access attributes of PAG vertices. The second example is a performance differential analysis pass. It is a comparison of program performance conducted under the independent variables of input data, parameter, or different executions. For example, for two programs runs with different process scale, the performance difference stands for scaling loss. Here is the code for the performance differential analysis pass. Append is a set operation, and three V metrics are graph operations. The last example is a contention detection pass. We leverage subgraph matching algorithm to detect contention patterns. For the subgraph pattern on the left side, it can identify all embeddings on the PAG. Besides, subgraph matching algorithm can be used to detect other performance bugs. Here is the code for the contention detection pass. Add vertices and add edges are graph operations to build a subgraph, and the subgraph matching is a graph algorithm. Then we introduce the high-level API. High-level API is designed for describing user-defined analysis tasks. There are three kinds of high-level API. First, PAG generation. PerFlow provides API to perform hybrid static dynamic analysis and generate PAG. Second, AFD construction. PerFlow provides APIs to construct AFD with built-in or user-defined passes. Third, reporting API is provided to show the analysis results as human-readable text or visualized graph. We use two examples to show how to use high-level API. The first one is a scaling loss detection task. We first run the program under different process scales. Through a performance differential analysis pass, we get the scaling loss of all code snips. And further, through a hotspot detection path, the severest scaling loss is obtained. Finally, we use a report API to show the results and their corresponding attributes. The second example is a communication analysis task. We first run the program with hybrid static dynamic analysis, then filter the MPI function, and then perform hotspot detection, imbalance analysis, and breakdown analysis. Finally, we report the results. The experiments are done on 10/2 supercomputer. Each computing node has 24 cores and 64 GB memory. We also use a local cluster for some experiments. We evaluate our framework with 8 programs in MPB benchmark and 3 real-world applications with up to 700,000 lines of code. The largest scale is up to 2,000 of processes. We also compare PerFlow with state-of-the-art tools, Scala, HPC Toolkit, MPIP, and Scalana. First, we evaluate the overhead of hybrid static dynamic analysis. Static binary analysis costs 0.77 seconds on average. The overhead of dynamic profiling is 1.11% on average, and the collected data costs 2.5 MB on average. Here we take Zeus MP as an example to show how PerFlow works. We implement the scalability bottleneck detection task in Scalana. This is the AFD of the analysis task. Only backtracking analysis path is user-defined path. Other paths are built-in paths provided in PerFlow. The results of differential analysis shows the scaling loss on the top-down view of PAG. And hotspot detection paths show that MPI functions and some loops are the severest scaling loss. On the parallel view of PAG, the results of imbalance analysis are marked as black boxes. The results of backtracking analysis are marked as red arrows. Finally, some loops are reported as scalability bottlenecks. We also compare PerFlow with some existing works. Implementation with PerFlow only need 27 lines of code, but the source code of Scalana is over thousands of lines, which prove that PerFlow can significantly reduce the complexity of implementation. Comparing with a tracing-based tool, Scala, PerFlow only incurs extremely few runtime overhead and storage cost. Besides, PerFlow can automatically perform analysis tasks, but profiling-based tool, HPC Toolkit and MPIP, still needs human efforts to detect scalability bottlenecks. We also perform different analysis tasks on other applications. For example, communication analysis on lamps and contagion detection on white. In conclusion, we have a core idea in this work. The process of performance analysis is a flow diagram. And in PerFlow, we present two-level abstraction, PAG and AFD, as well as two-level API to reduce the complexity of implementing analysis tasks. In future work, we consider to implement more insightful analysis tasks based on PerFlow. Thanks for your listening. If you have any question, please feel free to ask or contact me.